Okay, College Trig, bring it back for another video here. It looks like I might be just a little bit in your way, huh? Try that. Sorry about that, if that's been the case. Operations of complex numbers. We just left off by saying that z to the n is the same as r to the n. So you take that radius and raise it to the nth power, and then you take your angles and you multiply them by n. So what we want to do is, for our third example, and then we'll do a fourth one, 1 plus I root to 3 raised to the 20th power. Again, if you take 1 plus I root to 3, multiply that out 20 times, that's going to be rather ridiculous. So let's do the easy way. Let's do what De Moivre did. And let's first put it into what we call trigonometric form. So 1 plus I root to 3 is the same as, we need a radius and we need theta. Those are the two things that we need. In order to come up with the radius, what I do is I do square root of a squared plus b squared. And we get 2. Okay? So we have 2 times the cosine of plus I sine of. And we're going to need an angle then. And to find the angle, we said tangent of theta is equal to b divided by a. Where is the tangent of theta equal to the root of 3? Well, we said that's going to be at a 60-degree angle. If we set this up, tangent's positive in the first and the third quadrant. Which quadrant am I working in? Well, the first quadrant, because 1 plus I root to 3, that's going to be over 1 and up the root of 3. So 60 degrees, or pi over 3. Okay? So that's trigonometric form. Now I'm going to take that and raise that to the 20th power. So 1 plus I root to 3 raised to the 20th power. 2 to the 20th times cosine of, I multiply these by 20, so 20 pi over 3 plus I sine of 20 pi over 3. Okay, I'll just leave the 2 to the 20th alone. That's a really big number. But the cosine of 20 pi over 3 and I sine of 20 pi over 3, I can't leave the 20 pi over 3. So everybody agrees that 20 pi over 3, that would be a lot of times around the unit circle. I would agree. So what is 1 full revolution around the unit circle? That's 2 pi. Or 6 pi over 3. Sometimes people get confused by this because everybody agreed that those are the same. That 2 pi and 6 pi over 3 are the same. Okay, good. So then we'll just subtract off a revolution. If you take 20 pi over 3 and you subtract 6 pi over 3, you get 14 pi over 3. Is 14 pi over 3 more than once around the circle? Yeah, subtract it off again. 14 pi over 3 minus 6 pi over 3 gives me 8 pi over 3. Subtract that again. 8 pi over 3 minus 6 pi over 3, and I get 2 pi over 3. So turns out it's the same as 2 pi over 3. So I have 20, or 2 to the 20th, times the cosine of 2 pi over 3 plus I sine of 2 pi over 3. Good. So that's what we call a trig form of a complex number, okay? Now, the other thing you want to do is you want to place this into complex form. And so what we're going to need to do in order to do that is we're going to need to be able to determine the cosine of 2 pi over 3. 2 pi over 3 places you here. It's a 60-degree angle. On this side, 2 pi over 3, it's 120 degrees. And so this coordinate is negative 1/2 root of 3 over 2. So the cosine of 2 pi over 3, as I work to put this into complex form, I have 2 to the 20th times negative 1/2. Okay? And then root of 3 over 2, we are going to have plus I root of 3 over 2. Now, that's one way to write it. Another way to write it that's actually kind of nice is I could factor out 1/2. Watch what happens when I factor out 1/2. I get 2 to the 20th times 1/2 times -1 plus I roots of 3. And to just finish this off, 2 to the 1/2 is the same thing as 2 to the -1. What is 2 to the 20th times 2 to the -1? It's 2 to the 19th. So that's what we would say is complex form of a trigonometric number. So we got trigonometric form, we got complex form, did that tricky thing with the 1/2. I'm going to allow multiple ways of writing your answer. You'll see on the answer key for what I'm looking for, but that's a good result right there. Again, 1 plus I root of 3 multiplied out 20 times. It takes a long time. Boom, we made it pretty short right there, okay? All right, I'm at 6 minutes. Looks like I have 9 minutes left to do our fourth example. And I want you guys to know that I really believe as you're working through stuff, I think if you could do De Moivre's theorem that we're doing here, I think that that's really probably the most complicated stuff that you're going to see during this fourth quarter time. Doesn't mean everything else is easy, but I think that this is challenging stuff right now. So this is kind of where I said, okay, this is about as tough as we're going to get. And other stuff, as we cover other subject matter, I really don't think you're going to find it to be nearly as challenging. So let's try this this guy right here, okay? We're going to go 1/2. Actually, let's go -1/2 plus 1/2 I. And we're going to raise that to the 20th power. Okay? A 1/2. Instead of 20th, let's go 10th. We'll go 10th power. Okay, so this is example number 4. First thing we have to do is we have to put it into trigonometric form. So -1/2 plus 1/2 I. We're going to put that into trigonometric form. So I have the square root of -1/2 squared is a 4th. 1/2 squared is a 4th. So you get the square root of a 4th plus a 4th is a 1/2. The square root of 1 is 1 over square root of 2. Okay. Or in this situation, we just get the root of 2 over 2. So root of 2 over 2, that is my R value. Okay. Then let's move to our theta value. Theta, we set up tangent of theta is equal to B divided by A. So 1/2 divided by -1/2. If you take two numbers divided by themselves, you get 1. 1 is negative. So where is tangent of theta equal to? -1. Well, from your work, you should recognize that's a 45-degree angle. Which quadrant am I in? The quadrant is the second quadrant because it's back 1/2 and it's up 1/2. So I'm in the second quadrant. Okay. That's 135 degrees. And so that's 3 pi over 4. So theta is 3 pi over 4. Cosine of 3 pi over 4 plus I sine of 3 pi over 4. So just checking on my time, we got 6 minutes. What I want to do here is I want to raise this to the 10th power. Okay, I'm going to get rid of this stuff right here. I'm going to raise that to the 10th power. So -1/2 plus 1/2 I raised to the 10th power is equal to, we're going to take that guy and raise that to the 10th power. What I do is I like to rewrite the square root so that it's 2 to the 1/2 or 2 to the 1, and we're going to raise that to the 10th power. Times the cosine of, what do we do the angles? We multiply them by 10. So we have 30 pi over 4. plus I sine of 30 pi over 4. Okay, we got some simplifying to do here because we can't leave our answer like that. Power to a power, we have 2 to the 1/2 to the 10th. We multiply it, we get 2 to the 5th. On the bottom, 2 to the 1 to the 10th is 2 to the 10th. We can simplify that yet. I got 2 to the 5th over 2 to the 10th. Cosine of 30 pi over 4. 30 pi over 4 would be the same as 15 pi over 2. I think everybody here would agree that 15 pi over 2 is more than once around the circle. So 2 pi is the same as 4 pi over 2. So let's subtract off a 4 pi over 2. 15 pi over 2 minus 4 pi over 2 would be 11 pi over 2. Minus 4 would be 7 pi over 2. Minus 4 would be 3 pi over 2. Well, 3 pi over 2 is within that once around the circle. So I have the cosine of 3 pi over 2 plus I sine of 3 pi over 2. Works out quite nice. 2 to the 5th over 2 to the 10th. You can see that it's 1 over 2 to the 5th. Whoop, not 1 over 25. That was dumb. 1 over 2 to the 5th. And to finish things off here, that is what we call trigonometric form. If we want to do complex form, you have to figure out what cosine of 3 pi over 2 is and what sine of 3 pi over 2 is. Well, 3 pi over 2, you all know that places you right down here, and that terminal point is 0, -1. So you end up with 1 over 2 to the 5th times 0, and then minus 1i. So it turns out that this final answer is -i over 2 to the 5th, which is 32. -i over 32. Now, again, multiplying this out 10 times, I dare you to sit down and multiply that out 10 times. And if you do, it's really cool. I remember the first time I did it, and you're saying, well, you're crazy, Mr. Gens. To some degree, yeah, I want to be convinced that the formulas that we're given actually work. And so I remember when I was younger, I was in high school, and I saw it, and I'm like, does that really actually work? Because what that is saying is if I actually multiply that out 10 times, that I'm going to get exactly -i over 32. Well, first time I did it, I made a mistake. They didn't work out, but I found the mistake. And as I found mistakes, eventually, yeah, it comes out to be exactly -i over 32. It's intriguing how it works out and how we can make it so simple. But that's the beauty of de Moivre's theorem. What are the applications of this? The fact is that without imaginary numbers and complex numbers, we wouldn't be able to have the electricity service that we currently have. So we have alternating current electricity. We've gone over that. We've talked about that in class. So breakthroughs have been made in that regard. But there are other breakthroughs that we're looking to make as well. In fact, there's really kind of 7 of the foremost mathematical problems that we cannot solve at this time. And one of the most famous is called Riemann's conjecture, Riemann's hypothesis. And it's an amazing idea, and it has something to do with prime numbers. And the idea is that we don't know when the next prime number is going to happen. So we go 3, 5, 7, then we skip 1, we go to 11, then 13. We skip 1, we go to 17, 19. Then we skip 1, we go to 23. Then we skip 2, we go to 29. Why did we skip 2 there? How can you predict when the next number is going to occur? It's really, really challenging. But I can tell you that in order to prove when the next prime number is going to happen, it actually requires some complex analysis, which is pretty neat. This is at the heart of it. And they're wondering what other breakthroughs this might lead to as well. Have a great day. We'll put some other information up for you.